Okay, so today we're going to speak about an important statistical technique that enables going from a model that is not very predictable, it's not stable, to a model that is much more stable and predictable. This is a generic technique, and it doesn't require a specific assumption about the underlying distribution of the data. So it falls under the category of non-parametric techniques. Very useful. It's realized in machine learning in a variety of ways. You'll find it everywhere, basically. Like, for instance, with random forest and so on. And today we'll try to cover it a bit. So let me explain the setting and what I exactly mean by noise and getting rid of the noise, and that way we'll get a clear understanding of what I'm trying to do first, and then I'll explain how it's being done. In addition, this is a good precursor to another non-parametric technique that is often used in a variety of ways, and it's very fundamental and important in machine learning, which is called bootstrapping. So this is bagging, and bootstrapping will come later. So the setting is as follows. This is one possible setting, but let's take that setting first. It's a regression setting. You have n pairs of point x1, y1, xn, yn that we sampled from the underlying distribution and represent examples of the values that a function that we want to learn assumes at a point. So we assume that f of xi equal yi. So maybe think about xi as a list of different factors, and then we want to predict the temperature of something, doesn't matter. So it's a function from a vector of parameters, if you like, to a value. That's the meaning of this notation, a function from Rn to R, a function from a vector of values to some value. And we assume that we have some algorithm that attempts to learn the function. So given the endpoints we feed it that were sampled, we feed it into the algorithm, and we get what I called here GI, which is basically a function that estimates f, or if the algorithm is good, it estimates f. So that's our setting, a standard regression setting. Any questions about the setting or comments? Okay. So the crucial point about this is that, say I sample the data again. So I get another n points, n pairs of examples of the points and the value of the function at the point. And I feed it again into the machine learning algorithm, then I get a different GI. So because the data will be slightly different because the sampling is random. Maybe there's other factors, but that's the main thing I'm interested in now. So every time I sample the points and I apply my machine learning, potentially I get a different approximation to the function. So that's not a good situation. And if those candidates are very diverse, it's even worse. So there's some instability in the result that I'm getting that has to do with the process that I'm following. So it's fundamental to machine learning. Every time I apply the machine learning algorithm on a different data set, I get a different candidate. But I should, at least intuitively, you would expect that the candidates will be very similar, very nearly the same. You don't want them to be very different. Is that point clear?
One quick question. So what are the letters above the arrow on the right side that goes from left to right? Yeah.
Independent, identical and independent.
That denotes the sampling from X and Y.
Yeah, yeah.
Oh.
So the concept is that, at least theoretically, we are sampling endpoints independently from the same distribution. So the endpoints here represents the empirical distribution, okay? Sorry, represent the real distribution. The empirical distribution suggested by the point that we sampled, we basically assume that it represents the empirical distribution more. And that's a crucial assumption. And that's more or less the only statistical assumption that we're making here. Okay?
Okay, but we are just sampling X and applying a function on X that we sampled and we obtain Y, right? Or do we take X and Y as a pair?
For our purpose, it doesn't matter in some sense. I mean, you can think, if we had the function, we would not need to learn it, right? But think about the temperatures example. So we have all of these factors about some machine, okay, that we are measuring, and then we're measuring the temperature inside the machine, okay. So there's a relation. We believe that there's some relation, some function that, given those temperatures, those factors, gives a temperature. And we don't know what the function is, but we have measured that those pairs apply. Okay. Does that make sense now?
That makes sense, because I was trying to understand if F itself if that is deterministic, like do I always get the same Y if I apply on X, or if I don't, right? Or maybe that's
so that's a good question, and it could be that it's also random, but I'm not going there on purpose. I want to keep it simple.
Okay, got it.
But the same thing applies. I mean, even if it's, if f of xi is a random thing, then that goes into the instability as well. Okay. So
Oh, I see. Okay, got it.
okay, so you want to get rid of the instability that comes from a distribution that includes, it's your question basically boils down to be specific about the underlying distribution, the set on which the underlying distribution applies. So I could say, it applies only on the input, on the xi's, and then f is deterministic, you see? And then I could say, the distribution applies on x, the inputs, times y, the temperature. And then, so I have some distribution, and I'm trying to estimate that. In both cases, I want it to be a stable estimation. Okay?
Gotcha. Okay.
Yeah. The general setting, if you read the literature, will always say, well, most of the time we'll go and say, the distribution is on the Cartesian product of the input and the output. To be general. But it's easier to grasp the ideas here, disregarding it. And many times, actually, if you look at phenomena that we are interested in, the function is deterministic, and that's a special case. You see, it's a special case that many times it applies in practice, and that's what we need to do practically. But many times it's not the case. One interesting reason that it's not the case is when you don't have all the parameters in the input, so you have some variables that impacts things that you don't control. Okay. Okay. So you model it as a Cartesian product of the input and the output, the distribution in such cases. Compounded variables, they call it. Make sense up to now?
Yeah, thanks.
Okay, great. So that's the crucial thing to understand. And now, how do we deal with it? How do we deal? So that's the bagging technique. The idea is simple. And very expensive in practice sometimes, but you just resample and you take the average. So given some point, the average would look like this. If I sample k times, then given some point in which I'm estimating, I would get random behavior. I call that variable y. And then if I take the average, that random variable y. And if I take the average, then that's a way to make the result more stable. Now let's understand why. So clearly, to understand what I'm doing, what I'm going to do now, you need to be familiar with average and variance calculation. If you're not, just afterwards go to random variable in Wikipedia and read there. You'll see all the rules explained there about manipulating and calculating and working with averages and variance. But one thing is that the average is a what they call a linear functional. So basically, if you take the average of, if you consider the average of this, you would just get the average. Okay. So let me maybe, but that's not the point that I'm trying to stress. So try to understand what I said. The average of the average is the average. Try to understand it as an exercise. And if you don't get it, look at the lecture notes, and if you still don't get it, ping me. Okay, but let's focus on the variance. The variance, this is what we are interested in. If you look at the variance of the average, then 1/k goes out as a square. Any scalar goes out as a square. And because the measurements are independent, as we mentioned before, it's the sum of the variance. And then that cancels. So you have the variance of the random variable over k. And k, if k is large, this is just a number. Variance of the random variable is just a number, and over k, it goes to 0. So basically, that's the bagging idea. If you take the average, it becomes stable and it doesn't jump so much around, and the variance which measures the jumping around of the random variable kind of squeezes more and more and more and becomes smaller and smaller. There's a price. You need to sample many times, and that's very expensive for many reasons. You have to sample many times, and then you have to apply the model and get the value. But sampling many times or getting more and more data samples is in practice many times too expensive. So there's other techniques that we'll talk about later that try to overcome that. Any additional questions, comments? Okay, so thank you very much for joining today, and we'll continue next week.
Eitan.
Thank you, Eitan.
Thanks. Bye-bye.